Hello, I'm Tomoya Onodera from Shinshu University. I will present the topic entitled In-Hand Manipulation Exploiting Bending and Compression Deformations of Caterpillar-Locomotion-Inspired Fingers. Let me begin with the background of this study. In recent years, many soft robotic grippers have been proposed. Such a soft robotic hand is good for just grasping, but it's not dexterity. Human hands are made soft, and they are much more dexterous than conventional soft robotic hands and can perform in-hand manipulation, which manipulates a grasped object's posture. Incidentally, realizing this function with a conventional solid robot is very challenging. Therefore, we focus on the Caterpillar and propose a soft robotic hand that can perform in-hand manipulation. Caterpillar use only a few neurons to control their very adaptive movements. We thought that imitating this motion in a robot would allow for flexible movement with simple control system. And we thought that Caterpillar's peristaltic motion could transport objects like a conveyor belt. Here, you can see a video of in-hand manipulation or a prototype. When a robotic hand repeats the peristaltic motion like a caterpillar while grasping an object, you will see that it rotates an object like a conveyor belt. From here, I will explain the content of my research. Before fabricating the prototype, I conducted a simulation to verify whether it's feasible to use the peristaltic motion of the caterpillar to transport objects like a conveyor belt. I used mathematical models to simulate the peristaltic motion of caterpillars and elastic body. Here, linear springs, masses, dampers, torsion springs system reproduces these models. This is the result of the simulation. The green masses represent fingers that imitate the caterpillar's movement, and the black masses represent the elastic body. You can see the elastic body moves in one direction. I found that the finger masses can move the contact object in one direction when it not only moves peristaltic but also switches frictional force between two models depending on the direction of the finger mass's velocity. Next, I will explain hardware. The simulation results show that peristaltic motion and switching contact friction are essential for transporting objects by the caterpillar's locomotion. Therefore, we designed the robot's finger in two parts, a peristaltic mechanism and a frictional switching mechanism. First, I will explain peristaltic mechanism. The basic structure consists of multiple connected arcs, and the arcs are compressed to reproduce peristaltic motion. The drive method is a tendon-driven mechanism. The material is TPU printed by a 3D printer. Next, I will explain friction switching mechanism. Based on the simulation results, we designed a friction switching mechanism that changes the contact friction with the grasped object according to the movement direction. In this movie, when the peristaltic mechanism compresses, the high frictional area contacts, and conversely, when it extends and returns to its original state, the low frictional area contacts. Thus, the mechanism can move the grasped object by alternating contact with high and low frictional areas. This is an overall view of a robotic hand fabricated with the fingers as I explained earlier. I did an experiment that grasped some simple shaped objects by robotic hand. Experiments were conducted using cylinder and rectangle. High or low frictional force sheets are attached to the surface of each frictional switching mechanism, and three different manipulation patterns can be realized depending on which sheet is applied to the fingertip side or the base side. In the illustration, the red area represents high friction sheets, and the blue area represents low friction sheets. Pattern 1. The left finger has a high friction sheet on the fingertip side and low friction sheet on the base side of each friction switching mechanism. The right finger has a low friction sheet on the fingertip side and a high friction sheet on the base side. At this time, it can rotate the grasped object clockwise. Also, it can rotate counterclockwise by placing sheets on the opposite. Pattern 3. Both fingers have low friction sheets on the tip side and high friction sheets on the base side. So then, it can move parallel from the fingertips to the base side. We designed a soft robotic gripper to perform in-hand manipulation inspired by Caterpillar. Simulation verified proposed hypothesis that Caterpillar movements can be applied to object transportation. The prototype can rotate the grasped object in a particular direction with the finger's peristaltic movements. In the future, it is necessary to increase number of fingers to perform more dexterous manipulation.